So folks, in the last video we found we were given, or we constructed the ODE 1x double dot plus 2x dot plus x is equal to 6 cosine of t. That was our original ODE that we constructed for this spring mass system, and we just found that it had a solution. In fact, let me say a general solution. What we have listed up here, x of t equals c1 e to the minus t plus c2 t e to the minus t plus 3 sine of t. What we now want to do is actually give an initial value problem to this. So the way we'd phrase the initial value problem in this case is that we have an ODE, which we've just listed, 1x double dot plus 2x dot plus x needs to equal 6 cosine of t. There's our ODE. And then this is a second order initial value problem, so we need two initial conditions, and we need to see if we can glean that from the information given here. So we're told that it's released from equilibrium. So in that case, we're told that x at time 0, the position at time 0, is 0 because it's released from equilibrium, and it has an initial upwards velocity of 1 meters per second. Now this is where you can get into trouble. It doesn't matter how you set up your orientation, but you need to be consistent. And in our case, because I set up this distance to be a positive 10, then I had to choose my gravity to also be a positive 10, and we're considering moving downwards as a positive, and so then upwards would be considered a negative displacement. And so if we have a velocity of 1 meters per second upwards, then we would have that x dot of 0 is equal to negative 1. So now let's go ahead, now that we've talked about that issue, and that is kind of a little bit of a pain of an issue, to be careful with your signs there. It doesn't matter how you set up your orientation, but you need to be consistent. Let's now solve the IVP. Well, we've got the solution that I listed here, and so we know that x of 0 needs to equal 0, so that implies that 0 has to equal c1 e to the minus 0 plus c2 times 0 e to the minus 0 plus 3 sine of 0. And putting all that together, we get 0 has to equal c1. So we now know c1 is 0. Okay. As someone mentioned in class, it's going to be really helpful to, if we find one of those constants, it'll save us in our derivative calculations in some cases if we evaluate it at that constant. So notice that this term, even though it's true for, in general, for the solutions to the ODE, it is not going to be a term that shows up in our particular solution to our particular ODE because of that initial condition there. So when I go to compute x dot of t, I can just take the derivative of what remains. And so in this case, I'll have to do a product rule here. Here's the first times the derivative of the second plus the second times the derivative of the first. So it would be c2 times 1 times e to the minus t plus 3 cosine t, taking the derivative of that third term. So then we're told that x prime of 0 equals negative 1. So we have that negative 1 is equal to c2 times 0 e to the, let's see, actually there's a negative sign there. It's not going to matter, but negative e to the minus 0 plus c2 times 1 times e to the minus 0 plus 3 cosine of 0. And in this case, we end up with negative 1 is equal to, so those cancel, we're just left with a c2 there, and this would be 3 times the cosine of 0, which is 1. And I dropped a plus sign somewhere. There we go. And so we get that negative 4 is equal to c2. So putting all that together, folks, I've got my particular solution to this initial value problem, which is a spring mass system like the one we described in the beginning of the problem, together with these two initial conditions, and the unique, by the existence uniqueness theorem, the unique solution to this IVP is minus 4 t e to the minus t plus 3 sine of t. And here we have our solution. Something to keep in mind, that this should sort of make sense, is that the initial conditions give us the terms that show up in the homogeneous solution. And initially, this term right here is sort of dominating the picture of the spring mass system. But because of the dampening force in the spring, we eventually, this term right here will eventually be contributing to 0. And as t approaches infinity, x of t approaches the function 3 sine of t. And that's sort of interesting in this case. Anyway, there is our solution to this ODE. All right. I'll pick up in the next video, and let me know if you have any questions.